Uh, Hi everyone, thanks for joining me. My name is Alex, and today on a prep stream we'll be discussing about paper CPC by DeepMind. Uh, the title of the paper is Data Efficient Image Recognition with Contrastive Predictive Coding. Before we get into the paper itself, I'd like to begin with the backstory of why this particular paper is so important and like what motivated me to go ahead and read about this domain and this particular paper in general. So, a month ago, yeah, I along with Aviraj and Ankita, we worked on a paper. It was a competition, and we had to perform classification segmentation on high resolution aerial images in the challenge FedNet. And in that, one of the major problems that we had, as you can see here, was so the number of labeled images that we had were very low. So out of 1,500 almost images, we had only 400 of them labeled. So it's 20-25% of the images are labeled. So yeah, someone's speaking. So here's where actually our venture into semi-supervised domain started, and as you can see, we used a very simple semi-supervised uh, method where we generate pseudo labels from our model, and then we use those pseudo labels for training, like using the label data. We generate pseudo labels from the label data, and we go ahead. So this was a very basic approach that we did, and we didn't really get much time to venture into other methods and improve our accuracy. So after that, I started a course called Deep and Supervised Learning by UC Berkeley, and it's a very good course. It as the title suggests, it's about semi like self supervised learning or unsupervised learning. And in the first lecture itself, one of the slides really caught my eye, and that's we'll see what that is. So one of the motivations for unsupervised learning is we have lots of data which is unlabeled because it's very difficult, it's expensive and labor intensive tasks to get labeled. And what deep unsupervised learning would be is capturing rich patterns from raw data in a label free way. There is a very good quote by Jeffrey Hunter in 2014. He mentions that the brain has about 10 to the power 14 synapses, and we live only for about 10 to the power 9 seconds. So we have a lot more parameters than data. This motivates the idea that we must do a lot of unsupervised learning in the perceptual input, including proprioception, is the only place we can get 10 to the power 5 dimensions of constraint per second. So his main idea is that even as humans, we have a lot more parameters than we can absorb data, and hence there's some like we are lacking at having the same parallel in our deep learning paradigm, and we need unsupervised learning. We need to push unsupervised learning to get a better understanding of what actually understanding is. And there's a very famous uh, analogy by Jan Lepore. He mentioned how, like, for particular task, what are the given to a model, uh, what are like what's the comparison of the outputs that we expect from the model. So in a pure RL scenario, this cake would be a representation. The RL part would be the cherry on the cake. Because in an RL environment, pure RL environment, let's say we have a game. So you have all the visual features in front of you, but getting all the visual inputs, which are very high dimensional in nature, you still have to, like, your RL model just has to output a few bits of few bits of predictions, such as which direction it has to move with what acceleration and so on. In supervised learning, he mentions it's like the icing on the cake. So it could be, if it's a classification, then like all the labels are human generated. So if it's a classification problem, then it depends upon the number of classes, but it's still like 10 to about like 10,000 bits per sample. So if it's a classification, it could go like 10,000 for ImageNet, or maybe even more. If it's segmentation, then like you have to segment the entire image, and that could go till 10 power, like 10 power 4 prediction that you have to make for a particular input, and the model capacity has to be larger because it's making a lot more predictions. But in unsupervised or predictive learning, Yannick mentions that this like the output that we expect from the model is proportional to the entire cake itself, because as we don't have any human-based labels that restrict us uh, to train our models, we literally have the entire whatever data that we have, that we can expect as an output from these models in order to train them better. So example they have given here is if you have a video input, then in unsupervised domain you could uh, train your model to predict future frames in videos, and that will be millions of bits per sample. As we don't have any restrictions over dimensions because it's not human labeled or it's not a RL based environment, uh, we go towards more data oriented predictions, and that's unsupervised learning. As you can see, there are like lots of examples of how unsupervised learning or just generative tasks work better through the years. We'll get to the main slide, which will lead us to the people. Yeah. Uh, so in UC Berkeley, there was there were two professors, Mr. Malik and Mr. Ifros, and they had a bet. They UC Berkeley has been working uh, in the domain of self unsupervised learning, self-supervised learning for a long time, and they have good research in this. So there were two professors at UC Berkeley, Mr. Malik and Mr. Ifros, and they had a bet. So there's this competition or data set called PASCAL VOC dataset, which is a object detection dataset. So you have to give bounding buffers to the object in the image. And as we know, for object detection, we have RCNN architecture, which is a very decent baseline. So the bet was that if by the first day of autumn, October 23, 2015, so like this bet has been wide for 6 years now, but still it's pretty interesting. So if a method will exist that can match or beat the performance of RCNN on PASCAL VOC detection without the use of any extra human annotations. Human annotations in this case would be the label data. Uh, Without the use of any extra human annotations, example ImageNet, as pre-training. So you can't have like transfer learning, or you can't pre-train use pre-trained weights and then uh, do this detection task. Mr. Malik promises to buy Mr. Efros one gelato, which is two scoops of one chocolate and one vanilla. So this was a bet because everyone believed, and especially uh, the researchers at Berkeley as well, that it's we could get so better. We could just get as better. We couldn't get as better as the supervised tasks that we supervised models that we had, and we using semi-supervised or unsupervised approaches, we could get uh, we could push the limits, but it couldn't match or beat the supervised baselines at all. As you can see in this table, supervised baseline then was 74.7, and the higher the better. Uh, this this bet wasn't falsified till the year 2021, and in 2021 we got papers. One is Moko, uh, which got 74.9, which just barely slims over the supervised baseline. And we also got DeepMind's CPC V2, which literally crushes the supervised baseline, giving us 76.6 score on this object detection task. So this is very fascinating that we were able to surpass a supervised baseline, and this is the people that we'll be talking about today. All right. So data efficient image recognition with contrastive predictive coding. The diagrams in this paper are very interesting. So I see to it that I try to explain everything through the diagrams itself. Yeah, got it. So as you can see in this diagram, the shows percentage of label data. Okay. So what this represent? It's giving us top 5 classification accuracy on ImageNet dataset, and on x-axis you have label data or label data of ImageNet that was used, and this is the top 5 classification accuracy. Now the red one is the supervised baseline, and the blue one is the unsupervised baseline, which is CPC. And as you can already see that CPC is outperforming the supervised baseline at any point in the on the x-axis. So a few interesting points here would be with 100% of the label data, we'll see what how exactly these models were trained. But 100% of label data, you get better performance with CPC features, image features than raw exam. So 100% of label data, we have our CPC model, which is already trained in an unsupervised fashion, and those weights are used as initializations and then trained over the labeled data. And the red model, the weights are just initialized randomly, and then the model is trained over labeled data. So the blue one has pre-trained weights, but those pre-trained weights are trained in an unsupervised fashion. Okay. So given 100% of the labeled data for both these models, CPC with better initialization gets better accuracy every single point of the time. At 100% of label data, we get better results than the supervised benchmark. But most interesting thing is this is the x-axis is in a logarithmic scale. So at just 50% of the label data, you still your CPC model still performs better than the supervised benchmark at 100%. So we're using 2 times fewer labels on the ImageNet dataset. It's not a smaller dataset that we can't really we can get away with good results. It's the entire ImageNet dataset. So with just 50% of the labels, you still beat the supervised benchmark at 100% of the labels. And another interesting thing is with just 1% of the dataset of ImageNet, you get better performance than the supervised model at 5, like if it's trained on 5% of the label dataset. So like with 5 times fewer labels, it's still able to outperform the supervised model. So this is very fascinating. Like with 2 to 5 fold lesser labels, it's still able to crush the supervised models every single time. So that's what they mentioned, that 2 to 5 times less labels, and they show us how good they do on ImageNet dataset, and also, as we mentioned, PASCAL VOC dataset for object detection. So their motivation for this was deep neural network accelerate perceptual tasks when the label data is inabundant, but the performance degrades substantially when provided with limited supervision. But in contrast, humans and animals can learn about new classes of images from a very small number of examples. So there is some prior in our minds that we have some structural information about these uh, about uh, uh, our computer, like objects in general or the world in general. We have some prior information, and that helps us even with few labeled examples of newer classes. We are able to uh, pick it up better because we have some prior information. So we have in our brains a like structure representation of objects. So That's what they are trying to do with this unsupervised learning, that given just the unlabeled data, uh, the model will look at the entire data and build some structural representations of its own. And then after getting labels, it will be way easier for it to learn what particular image belongs to which class. So how do they do it? We'll get to the model. And before that, yeah, I think that the models then next thing which is important. Right. So they have an image, input image X. Uh, they they make overlapping patches of it, and then every single patch of it. So right now we are talking about how CPC is working to train the model in an unsupervised fashion. So this is the algorithm. So every single after making overlapping patches, every single patch is passed through a network feature extractor F theta. They're calling it. They are using ResNet 161 in this case. Don't need to pay attention. They further inform the different models they have tried and which one is the best. So they just pass it through a network, which in the end has polling layers. Hence, after passing through a bunch of layers and polling layers in the end, you get a vector, like one-dimensional vector here with some hidden dimensions, Z. They are calling it Z. And for every single patch, you'll get this vector for one image. After that, they use something called as masked convolution net. So what a masked convolution net is, in this scenario, in CPC version 1, they also tell us what improvement they made in version 2. So in version 1, you have the middle line of the image. The bottom part of the image is not considered when you're applying this convolution. So these vectors, uh, a group of vectors, let's say 3 by 9 vectors, are taken as input for this new network, which is context. They are calling it context network G. So this new network takes in these 3 by 3. We can call it a small image patch or feature patch, and then after passing through the model, they have another one vector representation. Now, what they are doing, as I mentioned, it's called a mask coordinate because we are masking out the bottom of the image and we are just applying this on the patches which are above the center. So once it generates a vector, they are calling it C. Now uh, they are trying to make a prediction. They multiply the C with a weight so that you get predictions, and like just as we have in classification. So you try to get a prediction of what vector, like uh, reflecting it through the center line, the part of the image that was masked, you still have the vectors generated through the feature extractor, and you're trying to predict what feature vectors are on the bottom of the image. So you train this by, you already have positive examples in this case. So feature vectors uh, which are on the bottom of the image are the positive examples, and negative examples would be from a different part of the image, so like right or left, or diagonally opposite or something, or even better, you have feature vectors negative examples from different images altogether or different class images altogether. And those feature vectors would act as negative examples. So given this positive example and negative example, it tries to predict which feature, what the feature representation should look like, and that's how it's trained. The feature representations have both these models, this feature extractor, context network, and another weight matrix that's set multi-time bit to make a prediction of which feature vector it has to choose. Or the entire pipeline is being trained on just the on just a cross entropy function, which loss function, which determines what the feature vector should look like at the in the same image uh, at the bottom. So this is the entire concept. So they trained this in an unsupervised panel because you don't need any labels for this. And after training it, uh, after it's completely trained on like all the unlabeled data, then you throw away the entire like the weight matrix here and the masked convolution network, context network G. You throw it away. Now you want to train this on like you want to initialize weights and train it further for label like fewer amounts of label. If you have 1% of image need 5% or 100% of the data set. So for that, what you require is just this network, which is feature extractor f theta, and the feature vector z. So you pass the image to this feature extractor again, same thing. You get this. So in this case, you have 3 7 by 7 dimensional image with some hidden dimensions across, and this is then passed through a, a new model. Would be a ResNet for this example, which whose weights are like randomly initialized. So the input, instead of being raw pixels, like we'll do in a supervised fashion, we'll input raw pixels to the network, and then it will be trained on all the labels, whatever are provided. We instead pass it through this model. We get this 7 by 7 by 4096, let's say, dimensional matrix, and we then pass this through our randomly initialized model, ResNet in this example, and then we train that on whatever number of labels that we have. And as you saw in the previous diagram, it performs very well on this. So unsupervised pre-training, uh, this is the pre-training. Unsupervised pre-training, 100% of images and 0% of labels are used. Images are 256, 256, 3-dimensional. Patched convolutions are used. So patched ResNet 161 is used as the feature extractor to get Z of 7 by 7 by 4096 dimensions. So this Z, this entire matrix will be 7 by 7, and the depth is 4096. So that's what represented here. 7 by 7 by 4096 is found. Then you use, sorry, I think I misspoke here. The patch is because it works in patches, and here masked coordinate because it masked down the bottom of the image is used here to abstract final vector C, which is again 7 by 7 by 4096 in dimensions, and then we train it on the loss function inference E, which is the same. We have positive examples, we have negative examples from other patches or other images, and then we train the loss function. Now evaluation. So after the supervised pre-training has been done, how do we evaluate this? So linear classification, you have 100% of the images and labels. Your pre-trained network is fixed in this scenario just because you wanted to, they didn't want the weights to change a lot or the representations of this self-supervised model to change a lot, to get a better and to get a clear understanding of how well the representations are without changing them. So 100% of images and labels are there, and you have again the passive ResNet and the weights are frozen. You just start the 7 by 7 by 4096 matrix, and then you pass it through a model which outputs 1000 by 1 dimensional, because this is an ImageNet task. We have 1000 by 1 dimensional output, and then you run through a cross entropy loss and you train just this linear model. This is one way of achieving some accuracy, and we'll see the metrics as we go through the paper. Second is efficient classification. So they tried different percentages of labels available from the dataset from 1% to 100%, and they removed the fixed. Oh, sorry, this could be either fixed or tuned, but and most of the diagrams that they have shown, they are also fine tuning this network. So the weights are not frozen in this scenario. Same images will be passed. You'll get some their feature representation. Then you pass it through a model, ResNet 33, and you do the same thing for entropy loss. Transfer learning. In transfer learning, uh, yeah. So you have your pre-trained effects routine, and in transfer learning, right? So as this pre-training is done on ImageNet dataset, they're calling it transfer learning because they are trying to achieve beat the accuracy on the object detection dataset, which uses a faster RCN model. So in that object detection task, we are using pre-trained weights from ImageNet. So we are having, as the title transfer learning, we have pre-trained weights, could be fixed or tuned, but they are fine-tuning it. And you pass it through faster RCN model, and the number of outputs would be less because it's a detection task, and you pass it through a loss, and you train the network. And this is the this pipeline was the one to beat the supervised faster RCN and benchmark by nearly 2%. And there's a baseline, supervised baseline. They have shown how they have trained it. So from 1 to 100% of images from the ImageNet dataset, yeah, they just have one network, ResNet 152, and you pass the image through this model, and then you run a cross entropy loss. All right. Now we'll look at the results after all of this training and the methodology. We'll look how good it performs. Uh, there's one thing, as we mentioned earlier as well, the benchmark given here, it's CPC V2. It's not CPC or CPC V1. We are mentioning CPC V2, which has beaten the supervised benchmark. This is so this paper would be about CPC V2 and improvement over CPC V1. So what exactly the authors changed from CPC V1 to CPC V2 is shown in the diagram. Yeah. So CPC V1, a linear classification accuracy, we saw in the first that they are freezing the model, and then they are training using those hidden representations to train another model. So linear classification accuracy, CPC V1 was around just above 50%, and they took it to well over 70%, reaching 75% by these increments. So first they increased the model capacity, that gave them some boost. Then they did bottom-up spatial predictions, that they gave some boost. Then layer normalization, random color dropping, horizontal spatial predictions, larger patches, and further patch-based augmentation. All of these together improved CPC V1 to CPC V2, which finally could beat the object detection benchmark, supervised benchmark. We'll see what they did in each one of these methods briefly. So in model capacity, they just tried larger networks, and in original CPC, they had only first three stacks of 101 ResNet. So what they did was, they converted the third residual stack of ResNet 101, which contains 23 blocks or 1024 dimensions. Instead, they used 46 blocks with 4096 dimensional feature maps. So instead of 23 blocks, they used 46 blocks, 1024 feature maps to 4096, 256 to 512 was mapped. And this was the network that they are calling it as ResNet 161. So this new architecture delivers better performance without any further modification. The model's expressivity is increased because its receptive field, as we saw, is increased a lot. So it could also deal with patches which are 80 by 80 pixels in dimension instead of 64 by 64. So this just switching the model from ResNet 101 to ResNet 161 increase the accuracy, top one accuracy by 5%, and increasing the receptive field increased it by 2%. Then they use layer normalization. So we can't really use batch normalization in this paradigm because, uh, as we said, we need to, the model needs to predict if what feature would be in the same image, and the negative samples would be collected from the other images of the same batch that we are constructing. So one main problem with batch normalization in all of the models that we have seen uh, is that to the batch statistics of what the mean is and uh, what other batch statistics are. It is able to uh, traverse information, and the model can somehow uh, learn a way to defy the loss and get better prediction because it has access to the entire batch. So batch normalization is not usually recommended. This was the entire motivation for the paper NFNet that came in and got state of the art results when it was released on ImageNet dataset. So instead, they use layer norm in this case. They mention the same thing. Dependency between patches through the batch statistics can be exploited by to bypass the constraints of the on the receptive field. So instead of batch normalization, they do layer normalization. So instead of uh, normalizing over the batch dimension, you have hidden dimensions. So you perform normalization across the layer dimensions, and that gave them 2% increase in accuracy. They also added prediction lengths and directions. So large, like this is a large architecture. From 101 they shifted to 161. So it was a very huge architecture. And as we mentioned earlier in Jan LeCun's analogy of Lee K, uh, the amount of predictions that we have to do in unsupervised is greater than supervised and is greater than reinforcement learning. So the model capacity has also need to increase with every single task. When unsupervised learning, you will have larger models because they have to learn deeper representations because the tasks are harder and they need to construct representations from very abstract things, and it doesn't have a specific label or task to predict and make its way to like as in the case of supervised learning. So larger architectures are used, hence they run at a greater risk of overfitting. The authors address this by asking more from the network. So we are using larger network, it could overfit. Best way of not making it overfit is to get more information from it so that it uses up all the parameters that it has. So in V1, only uh, like top patches were used to predict what the bottom patches would be, but they added every single thing. Yeah, we repeatedly predict the same patch using context from below, the right, and the left using separate context networks. So the context network that we saw earlier, this context network, which a, which uses a masked connet, you have different context networks for all the four cases, and you ask all of this information or all of these predictions from the network. Yeah, yeah. So using separate context networks, we ask this like predict bottom, left, right, and top patches from a single patch, resulting in up to 4 times as many prediction tasks. So the number of prediction tasks increases. Now additional predictions. Uh, just adding the bottom up prediction increases the accuracy over C1, so V1 by 2%. But if you use all the four spatial dimensions, then the accuracy is increased by 2.5%. Then patch-based augmentation was used. Obviously, if the network can solve CPC using low-level patterns, it need not learn semantically meaningful context. Augmenting the low-level variability across patches can remove such cues. Even in normal computer vision tasks, we face this problem, and hence we perform some methods pre-processing so as to remove these low-level cues. To that effect, the original CPC model spatially jittered individual patches independently. We further this logic by adopting the color dropping method that I mentioned earlier, which randomly drops 2 out of the 3 color channels in each patch. 2 out of the color channels in each patch, and finally to deliver this, there is a dramatic 3% increase in accuracy just by using this method. They continued by adding fixed generic augmentation schemes uh, by a couple of papers, such as sharing rotation, as well as random elastic deformation and color transformations. And they got 1.5% more jump over the accuracy, giving it a total of 4.5% total accuracy. These augmentations introduce some inductive biases about content preserving transformations in images, but we do not optimize them for downstream performance. Uh, so these were all the methods that were used. So model capacity was increased, bottom up spatial predictions, bottom up and left right. Then layer automation was used. Random color dropping 2 out of 3 channels were dropped. Horizontal spatial predictions were used. Larger patches were also used when we moved from 101 to 161, and patch-based augmentations were performed. All of that gave V2 huge performance increase over V1. Now, getting towards comparison with previous state of the art. Let's just look at the table that they have provided. Yeah. So ResNet 200 train on pixels, ResNet 33 train on CPC features, gain in data efficiency. Similarly here, this one would be top 1% accuracy, and this is top 5 accuracy. And this is the percentage of label data that was used to train both ResNet 200 and ResNet 33. 200 was trained on pixels, 33 was trained on the CPC features that were obtained from the unsupervised model. As I mentioned earlier, it not just crushes our CPC model, not just crushes the supervised benchmark at 100% data by 3%, but with 50% less data, it still gets 1% more accuracy, which is top 1 accuracy in ImageNet. So it gets 81.2% accuracy with 50% of the labeled data. And another metric is here with 5% labeled data on ImageNet. This model performs 50.6% accuracy, top 1 accuracy. But just with 5 times less label data, you get 52.7% accuracy with CPC, getting over 2% performance gain. And this is over 1000 passes. So the any increment, any small amount of accuracy that increases, like it's a very big thing. Similarly, with top 5 accuracy, we see the same thing. We have more 1.3% increase in 100% labels, but with just 50% of the data, you get 0.4% more accuracy. Similarly, here with 5 times less data, you are still getting 3% more accuracy. Now they mention that they use ResNet 200 for purely supervised ResNet. They tried different models, but ResNet 200 performed the best. And their 161 CPC was pre-trained, and 33 was used for downstream classification. Now they compare the number of parameters here. ResNet 200 has approximately 60 million parameters, but so the supervised benchmark, it has only 60 million parameters, but they are ResNet 161 plus ResNet 33 has combined over 500 million parameters, and majority of these parameters are coming from ResNet 161. As we mentioned earlier, unsupervised models do require a lot of parameters, and not just being deep, but the input capacity was also wider in this case, and the number of parameters increased dramatically. So the combined parameters was 500 million parameters. But even if you freeze this model and just take the output from this and then run a resonance 33, your training will be faster. In a purely supervised fashion, yielded results that were similar to other unsupervised representations. So they also compare it with different implementations and how it performs. So we'll see in this table. So label data, top 5%, top 5 accuracy. Yeah. So we'll be comparing top 5 accuracy. All the other models, pseudo labeling, all the models that are mentioned here. When you use this particular combination, then only you get results which are equal to CPC v2, which is fine tuned. So they provide here CPC v2 fixed, so the resonant 161 is fixed, and it's not fixed, so it's completely fine tuned. Your fixed CPC v2 touches all the benchmarks given here, apart from this combination, which gets 91.2. But in all the other cases, even if you have a fixed network, you train just resonant 33 over the entire ImageNet data, you'll get better accuracy than any other, even the supervised benchmarks or other semi-supervised or self-supervised models that were trained. And obviously, fine-tuned will crush all of that. So the results were on par or with even stronger than strongest of the results. After all of this, in summary, they find that CPC provide gains in data efficiency that were previously unseen from representation learning methods and rival the performance of the more elaborate label propagation algorithm. So one thing in the first image, it's in the first diagram itself, is that as as we move from 100% of the labels to fewer and fewer labels, this is pretty constant. Like this is not decreasing dramatically. But if you're not using this method, then your accuracy goes downhill pretty quickly. So if you have fewer labels, then training a CPC v2 based model over your even if you have unlabeled data. So training it over unlabeled data and then using it over the whatever labels, few labels that you have, you'll get significantly better results by this method. So this was one of the best results out of this paper. So after doing all this analysis over ImageNet, they decided to try the image detection on PASCAL VOC 2007. It has 5,000 labeled images. They obtained 74.7% MAP. This is the same table that we saw in the slides earlier. So CPC V2 gets 76.6 over 74.7 supervised baseline. MOPO also performed uh, better than the supervised baseline, but it was just 0.2% increase. They they mentioned that their motivation further going is that this could be very beneficial in medical imaging and robotics because of the constraint in labels or data altogether. And they also the paper also shows that from going from V1 to V2, there were very small improvements that were changed, such as augmentation, optimization, network architectures, and all of that gave them a very big boost. So, focusing more on smaller details will give you a huge increments in accuracy is another peak that they have, and they mentioned that we they have tried the paper on images only, but it could also be used in NLP, audio, video, robotic and manipulation. So that is all for the people. If the panel has any doubts, we could take it. You guys are able to hear me? Can someone acknowledge that?
Yes, sir.
Yeah.
Yeah. If anyone has any questions, we'll take that. That would be all for the today's stream.
Not question, but that was a really nice presentation, Sahil. Thank you.
And thank you so much, Ankit. I think we if we had known this earlier and we had the time, we could have tried this approach for people would have been selected. But it was surprising that the teams ZDN from the ZDN University, those were selected for the FloodNet CVPF. None of them used any self-supervised or unsupervised method. So uh, like there is a scope there that could be exploited, and we could see how good like these not just uh, this paper CPC V2, but there are even better methods like Sinclair V2, and according to the availability of the models and the constraints that we have, I think we still have some scope to push this margin, like push the accuracies in that particular competition.
Yeah, true. I mean, yeah, I mean, none of the papers, although it was just two papers, so we don't know what rest of the
Yeah,
teams went for.
yeah.
But yeah, they didn't use any of this, so definitely worth trying, I think.
Great. Thank you everyone for joining. With that, we conclude our stream. Let's stop streaming.